All right, so this video we're talking about exponential decay. So some examples you'll hear about half-life, population decreasing, or values depreciating, or the depreciation of value. That's a big word. All right, so exponential decay, quick review of exponential growth. So exponential growth was y equals a times 1 plus r to the t, where a was the starting value, r was the rate as a decimal, and t is the time. Then we talked about compounded interest. So I've got the principal, and I've got 1 plus the rate over the number of times it's being compounded. So the power of nt, which is the number of times it's being compounded times the number of years. Okay, so that's growth, right? In both situations, you're earning money or you're paying interest, it's increasing or it's growing, okay? So today, exponential decay occurs when a quantity decreases by the same rate each time period. And how it's going to look a little bit different is this time it's going to be a times 1 minus r to the t. So that's the big difference to tell whether it's exponential growth or exponential decay. Okay, growth, I'm adding that rate because it's going to get bigger. Decay, I'm subtracting that rate because it's going to be getting smaller. All right, so the A, the R, and the T all stand for the same thing. So A is the original starting amount, R is the rate, the percent as a decimal, and T is the time. So here's an example. The population of a town is decreasing at a rate of 3% per year. In the year 2000, there were 1,700 people. Write an exponential decay function to model this situation. Okay, so let's write our function. So we got to start with our A, which is our initial amount. So at the beginning, there are 1,700 people in the town. Okay, then I've got 1 minus, because it says it's decreasing at a rate of 3%. So I've got 3%, which means my R is 0.03. Okay, and I'm subtracting that, and then I'm raising it to the power of t, right? The function, we do not plug in the values, we just use it in terms of t. Okay, then I want to find the population in 2012. So how many years have gone by from the year 200, or sorry, the year 200. From the year 2000 to the year 2012, it has been 12 years. All right, so I've got my 1,700 times my 1 minus 0.03, and now to the power of 12. Okay, so we take that and we put that in our calculator. So I got 1,700 times 1 minus 0.03 to the 12. Okay, and I get 1179. So we usually, it depends on what we're talking about, but if we're talking about money, we'll round to 2 decimal places. But I'm talking about people. We don't really have half of people. So we'll round to the nearest whole number. Okay, so when I look, I have 1,179.5. So it's over half. I'm going to round up to 1,180. Okay, so after 12 years, there will be 1,180 people left in the town. Okay, so another application of exponential decay, kind of just like with growth, we did compound interest. With exponential decay, we do half-life. Okay, so half-life is the time it takes for 1/2 of a substance to decay into another substance. So you may see this in chemistry. You kind of think about like half-life, substances decaying over time. All right, so the equation of half-life is A equals P times 0.5, right, where 0.5 represents like half of the life, right, to the power of T divided by H. Now, T divided by H is all in the exponent. So A represents the final amount after a certain amount of years. P represents the original amount. T represents the time. And H represents the half-life time. Okay, so the key to this is these must be the same units. They must be the same units. So if the half-life time is in seconds, then whatever other time you're doing must also be in seconds. So we can talk a little bit about some unit conversion as we go through this as well. Okay, so here's an example. I've got some chemical element, astatine, 218, and it has a half-life of 2 seconds. So I want to remember 2 seconds, right? That is my T, I guess I should use, or that is my H, right? My half-life, oh, I have the right color. That's my half-life time, okay? So all the other things that I need to be doing also must be in seconds, okay? Find the amount left from a 500-gram sample of astatine 218 after 10 seconds, okay? So I want to find A, and that's equal to the initial amount, okay? So it's saying I've got 500 grams. That represents my initial amount of astatine. And then I'm talking about half-life. So I'm going to have 0.5. That's part of my formula. It's halving. Okay, and then T is the time that I want to find it after, right? So this is 10 seconds. So that means I would do 10. And then H represents the half-life time. So 10 divided by 2. And that's all like up in the exponent. Okay, so let's plug this into our calculator. Again, with these exponents and such, we will have to be using some extra parentheses. We've got 500 times 0.5 to the power of, now I'm going to put the exponent in parentheses, so 10 divided by 2. Okay, and I get 15.625. Now we want to know, what does that mean? Okay, so if I started with 500 grams and the half-life is 2 seconds, then after 10 seconds, I have 15.625 grams of AT, or the astatine 218. Okay? All right? So let's look at another example. It says find the amount left from a 500-gram sample of astatine 218 after 1 minute. So this one's going to look a little bit different. My starting value is still 500, and I still have 0.5 half-life. But when I think about the T, the time, the units of this time have to match the units of my half-life, okay? So that means I have to convert 1 minute into seconds. So 1 minute, kind of an easy one, hopefully, is 60 seconds. So that means I'm going to do 60 for my T, and then still divided by 2. Right? So now we do 500 times 0.5 to the power of, in parentheses, 60 divided by 2, and we get a really small number. So this is actually a kind of a good opportunity to learn what this means, because we see this all the time. So if I have 4.65 e to the negative, what was that, negative 7? Okay, what that really means is 4.65 times 10 to the negative 7th power And it's saying that this decimal is so small that I can't fit it all in my window. So I'm going to give you this notation. Okay, and what this means is the actual decimal is 7 spaces to the left. So if it's a negative exponent, it's to the left. If it's a positive exponent, it's to the right. So there is 0.000004 grams of AT left after 1 minute. So tiny, 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 tiny amount. So here's another example. So I've got cesium-137 has a half-life of 30 years. Find the amount of cesium-137 from a 100 milligram sample after 180 years. Okay, so I've got my A, and I find that by doing my initial amount. So I start with 100 milligram sample, okay, times 0.5 to the power of T, okay, which is the time that I'm looking for. So 180 years would be my T over 8, which represents the half-life time. And I want that in parentheses. So I get 100 times 0.5 to the power of, in parentheses, 180 divided by 30. You get 1.5625. And we have to know, what are our units? So if I start with a 100 milligram sample, after 180 years, now I have 1.56 milligrams. Which I'm pretty sure is mg, but I don't know, so I'm just going to leave it in milligrams. Okay? All right, so a little summary. We've got exponential growth, exponential decay. The main difference between those two, growth is adding, decay is subtracting. Okay? Then we've got compound interest. So think about exponential growth, excuse me, with the extra n, right? The number of times it's being compounded. And then half-life, you can always just think of half-life is the one that has the 0.5. So if it's got 0.5, then we're talking about half-life. And now that I see this, I notice that it's missing the H. All right? So there's kind of just a quick summary again on the test. It will give the equations without their names. So you have to be able to look at it and identify what equation it goes to or what you're trying to solve for.